welcome to another video by Ivy Shubs. And today we are going to be doing parametric equations, vector valued functions, and polar curves, including polar coordinates and all the good stuff. So this chapter accounts for about 11 to 12% of the Calc BC exam, and we are going to jump straight into memorizing some formulas that are important, and then we'll do some polar curves, and then we'll follow it up with questions. Okay. So the first two formulas are about parametric equations, which are basically, as you can see, these are basically derivatives that are being differentiated with respect to t. Now you could see these in questions regarding a bit of kinematics, like questions on speed, velocity, and acceleration, which are in with respect to time, where you have to differentiate or even integrate with respect to time. So you can use parametric equations there to find dy by dx. And for your double derivative, you have to use this formula right here. Okay, so in the last session, during the last video, we came across a formula for the length of a curve, the length for any curve. Right now, we're going to see the length for a parametric curve. So this curve is defined by parametric points instead of your normal rectangular coordinates. So this is the formula. You basically have to memorize all of this. You don't need to know anything in detail or depth about them. It's all about the formula. So this is the formula for the length of a parametric curve. Now we're talking about vector valued functions, and I'm just going to show you the application. So your f of t would be in the form of something like this, right? You would have two angular brackets, and you have x of t, where you would have your x coordinate, and y of t, where you would have your y coordinate. So, and if you were to, let's say, find the derivative of f of t, that's f prime of t. So you would find the derivative of x of t, comma, the derivative of y of t. Now, if you had to integrate f of t, you would first integrate x of t and then integrate y of t. So it's really basic, it's very easy. There's nothing complicated about that. Now it's the slope of polar curves. Here, now we're going to start talking about polar curves, and we're going to follow it up with some examples. And basically, you need to memorize this whole formula. There's nothing to it. There's no derivation or anything. You need to memorize this. So that's the slope for any polar curve. Okay, now here are some questions. So this is a question of parametric differentiation. Your x is 3 cos 2 pi t and y is 4 sin 2 pi t, and you need to find dy by dx at t is equal to 1 by 6. So you input all these values in the formula and it's dy by dx, so you need to find the derivative of y first in the numerator and next the derivative of the denominator, that's x, later, and then you input the values and your answer should be negative 4 by 3 to 3. Now, yeah, so we have a question kind of like physics, right? It involves kinematics. So your position of a particle is described by two equations in x and y axis. So for your x of t, you have this equation right here, and for your y of t, you have this equation right here. So the first thing you do is find the velocity in the y direction with respect to x. This hints at finding your dy by dx. That's use parametric differentiation, since the derivative of distance is velocity and the derivative of velocity is acceleration. And to go from vice versa, you need to integrate it, right? And the second question is to find the acceleration, which is the derivative of the velocity. So first you need to find a, then you need to find the derivative to find v, right? So here are these equations. We'll find dy by dx, and to find the acceleration, it's going to be the double derivative, that is d square by y by dx square, and this should be your answer right here, and you need to find it at t is equal to 1. So you'll input the values and your answer should be almost this, right? Okay, so now we need to find the length of a curve with the parametric equation for x sine t and for y is equal to cos t. And we need to find it from limits 0 to pi. We'll input all these values, we'll differentiate it with respect to t, and we'll solve it to get an answer as pi. Okay, now we have vector valued functions 6t cubed plus 5t squared, and we need to find f prime of t. It's very easy. Find the derivative 60 cube is 18t square and 5t square is 10t. That's your answer. Okay, now we are going to find the integral of a vector valued function. So we have the same f of t as the previous question in fourth, that is 6t cube comma 5t square. And we are given some other information. And if you're wondering why we are given the information that f of 0 is equal to 3 comma 5, it's to find the constant when you integrate it, because you're going to get different constants c1 and c2 when you integrate x of t and y of t. Right. So you integrate it as normally and you get 6t to the power 4 by 4 plus c1. That's your first constant. And 5t cubed by 3 plus c2. That's your second constant. So to solve these constants, we'll input the values that we are given in the question uh, formally. We'll input the values and we'll get C1 and C2 to be equal to 3, comma 5. And now we're going to input this in the integral that we calculated and we get the answer as 6t to the power 4 by 4 plus 3, comma 5t cube by 3 plus 5. And that's your answer. Okay, now we're going to move on to the polar curves. That is the majority of this chapter. So, uh, memorize this formula. It's a very important formula. Area bounded by polar curves. We're going to discuss what polar curves are, what polar coordinates are. But first, just memorize the formula. Area is equal to half times the integral of r squared dot d theta with limits a to b. Now here r does not represent radius like how we saw in washer methods or disk methods or in the previous chapter. No, here r is a function of theta. So it's your normal, like you have a function in x or function in y. This time you have a function in theta. So yeah. Now we are gonna encounter another formula where you need to find the area bounded by two different polar curves, right? How we found it in the previous chapter. So this time it's half times r square minus r1 square dot d theta with limits a to b. Now let's jump into example questions. Okay. So I'm not going to show you the diagram first. We'll first see the question and then we'll go to the logic of how you make the diagram and how you find the limits. I repeat, finding the limits is probably the most important part because finding the limits is the only non-intuitive part of this topic, in my opinion. Everything else, like R, is already given to you and you can solve the integral on your own. It's not a hard integral and you can do it on your own, but finding the limits is where it gets tough. So we need to find the area of the region enclosed by r is equal to 4 sine theta. Here, this is your function in theta. Since there's no x or y term, it depends. Your theta is variable and your function will change accordingly to your change in theta. So this is the diagram for this. This is the graph. But how are you supposed to plot a polar curve like such? So equation in R, it's 4 plus 4 sine theta, and here 4 represents your radial distance from the origin. So basically your radial distance is going to be the distance you're going to start out from. So here I'll use some other color, right? Let's use blue. Okay, so this distance is going to be 4, and then you have your theta equal to 0. You're going to start from here, right? Or you could also call it kind of like the minimum distance, since your distance is never going to be less than that. Instead, when it's minus. Right. So now we need to plot all the values using a table on the graph. So that's what we're going to do. We're going to draw a table. I'm going to plot all the values on the graph. So here I have a lot of values for theta, corresponding values for sine theta, and input all these values in the equation to get all of these values. Now we're going to plot all these values in correspondence with the angle they make. So let's say on 0, it's at a distance of 4. So when it makes an angle of 0, like right here, it should be a distance of 4. When it's at pi by 2, it should be at 8. So this distance should be 8. This should be 4. And let's say at pi, it should be 4. So right here, it should be 4 as well. And let's say 3 pi by 2. At 3 pi by 2, it becomes 0. That's where the graph comes back to the origin. So the distance here is 0. Right. And this like polar curve is called a cardioid. And we're going to go in depth with that. So if you wanted to find the limits for this, you could see that this graph is starts from zero and it comes back to the same point. So you could say it goes from 0 to 2 pi, and those are your limits. This is going to from 0 to 2 pi, and you can calculate r squared or d theta. That's how you calculate the area for this whole cardioid, right? So here are some types of polar curves, right? These are your polar curves, and you won't encounter these three in my opinion. I haven't seen them, but it's good to at least gain some information about them. So you have, of course, your circles, and you already know about this. You have your cardioids that we just encountered. You have your one loop limicons, inner loop limicons, and lemniscates. Now, in your limicons, they might ask you to find the area for this inner loop, that is a green region right here, instead of the outside region. So finding the limits is very important, right? Since this loop doesn't go from 0 to 2 pi, it doesn't, it's not in all the quadrants for it to go to 0 to 2 pi. So the limits here would be from minus pi by 4 to pi by 4, but it might differ in for different limicons. Okay, so now you can always, kind of get a vague idea of the polar curve seeing the equation itself. For example, right here, the equation was 4 plus 4 sine theta. That's a cardioid. But if you didn't know that it was a cardioid, they hadn't told you, how would you know? Well, your equation is of the form of a plus minus b cos theta or a plus minus b sine theta. This is for your cardioids and limicons, not for your lemniscates or rose curves or Archimedes spiral or anything, right? So if your A and B are equal, then it forms a cardioid. If your A and B, if your if the A upon B is in the interval 1 and 2, right? Then it's a one loop limicon. And if your B is greater than A, then you have an inner loop limicon. For a lemniscate, the equation is in the form of a square cos 2 theta or a square sine 2 theta, right? And in lemniscates, they might ask you to find the area of one loop itself, for which the limits are going to be from negative pi by 4 to positive pi by 4, right? And the biggest part of this chapter is to, of course, practice, practice, practice. So here are some questions. You can pause the video, solve them on your own, and I'm going to show you the solution. Okay. So we need to find the area inside this equation, 4 plus 2 cos theta. And this is, of course, a limison, right? It's a one loop limison. It's 1 by 4 and 1 by, it's 2, sorry, it's 2. And it's still going to be a limison only, no need to worry. So for a limison, your limits are from 0 to 2 pi, and we can check that by plotting as well. This is a rule of thumb, so it's better to memorize these. So you plot all the values, you plot it all on the graph, and it runs from 0 to 2 pi. We integrate it, and finally we get our answer as 18 pi. Okay, now let's find the area inside one loop of r squared is equal to 4 cos 2 theta. Now, this is of course a lemniscate, and we need to find the equation for just one of these loops. That's this area right here. So to find the area, volume, right, to find the area, we input all this into the equation, and we'll, of course, this graph basically goes from minus pi by 4 to positive pi by 4. So those are going to be our limits, and that's how we're going to solve. You can also solve it from 0 to pi by 4, but then you would have to multiply it by 2 as well. And so your half will be cut out, but that's a discussion for another topic. And our answer should be 2. Okay, final question. Find the area inside the lemniscate r square is equal to 6 cos 2 theta and circle r is equal to root 3. So solve the question. Okay. So this is we are going to be a figure. I need to find the area inside the lemniscate. That's this area right here, and the circle r is equal to root 3. So we need to find this area, right? Find this area, and then we would need to double it to get the total area. So the limits are going to be from minus pi by 6 to pi by 6 this time. And how are we going to find that? Now, your normal limit gate was from minus pi by 4 to pi by 4. But this time it's pi by 6 to minus pi by 6. So how are we going to figure that out? Well, you basically need to equate both of these equations, and then you will get your cos 2 theta is 1 by 2, and your theta then belongs to pi by 6 or minus pi by 6. Right. And that's how you find the point of intersection, or you could say the angle of intersection for these two curves. Right. So you input all these values and you get the answer as 3 root 3 by 2 times minus pi by 2, and then you're going to multiply it by 2 to get 3 root 3 minus pi for your total area of the region bounded by the circle inside the lemniscate. And that's all for today. And thank you for watching. And be sure to subscribe and like the video. We have just one chapter left in the series, that is sequences and series. And after that, we're going to go back to some in original chapters like contextual differentiation, integration basics, and all. And that's it for today. I'll see you in the next video. And goodbye.